In Physics 30s. In today's lesson, we're going to continue to talk about key physics principles that we're going to need to make use of at some point later on in Physics 30. And the focus of this lesson today is going to be on the principle numbered 2. So the one that's referred to as uniform circular motion, where F net is directed radially inward. In terms of when this physics principle applies, and we're actually going to use this later on in the magnetism unit. Again, not totally clear like what this has to do with magnets, but you'll see. This applies to situations where, first of all, objects are moving in a circle, and they're moving in a circle with a constant period. Now, in terms of what a period is the time it takes for you to go through one revolution. So just the time it takes to go around the circle one time. And the word uniform means that that period has to be constant. So for example, if you were like on the bottom of a Ferris wheel and it took 30 seconds for you to go around the circle a single time, on the next repetition, you would also have to take 30 seconds to go around the circle for the motion to be described as uniform circular motion. Now, when an object moves in uniform circular motion, we'll show a diagram for this in a moment, but the velocity of the object is tangent to the circle in terms of its direction, and the net force, which we're going to give a special name for it. We're going to call it the net centripetal force. The word centripetal means center seeking. So both the net centripetal force and the acceleration point towards the center of the circle. So for example, we might have a situation, I'll just like draw it on the diagram here. So say we have like a rubber stopper and it's attached to a string, and someone takes this rubber stopper and they just start to swing it around in a circle that from our perspective is the clockwise direction. So the velocity is tangent to the path. Again, that word tangent just means it's a representation of the slope at that point. And if you want to think about this, if you're spinning this rubber stopper around in a circle and say like you were, for example, to cut the string at this point here, then the rubber stopper would fly out of the circle at a direction that is tangent to the circle and accounting for like what the actual rotational direction is, which is counter or clockwise in this scenario. Now, the centripetal acceleration and the net force, which again, we call it the net centripetal force, no matter where you are in the circle, that force always points towards the center. Now, just to clear up a misconception, just because the acceleration is towards the center of the circle does not mean that the object is going to just automatically go towards the center. The reason it doesn't do that is because, for example, at an instant right here, maybe we can call that point 1, it's moving. So what acceleration does is acceleration is all about how your velocity is going to change. So at the very top of the circle here, your velocity is tangent to the circle towards the right. The acceleration is towards the center. The acceleration wants to make it so you're eventually moving in a direction that's towards the bottom of the page. But since you're already moving, it takes a little bit of time to do that. So by the time you get over to this position here, which is position number 2, then that acceleration vector has caused your velocity to change. So your velocity is now pointing towards the bottom of the page, but then now your acceleration is towards the center. And then, so the acceleration wants to make the velocity change again. And this is what just continues to allow this circular motion to occur. So velocity acceleration, net force, this is what it would look like for an object that is moving in a clockwise direction. And specifically the vectors you see in the picture there are when you're located at the very top of the circle. Velocity is tangent to the path, and the acceleration and net force or centripetal force always point towards the center. That's why it's called centripetal. It's a center-seeking force. In terms of mathematical equations you can use, there's a couple additional kinematics equations. So if we want to calculate the speed, so we have the absolute value of the velocity vector. So again, the direction is just tangent to the path. That's equal to 2 times pi times r. R is the radius of the circle, and then t, as already mentioned, or not already mentioned, but t is the period, which is the time it takes to get around the circle once. So you have 2 pi r over t. That's on your formula sheet. You also have equations for centripetal acceleration. So you have the magnitude of your centripetal acceleration can be calculated by v squared divided by r. And again, that's your speed, which the object is moving. Or you can calculate it by 4 pi squared r over t squared. The first variation of the equation, this one, is useful if you know what the actual speed of the object is moving in a circle. And this equation is more useful if you know what the period is and not the speed. But you can convert between the two of them just by using equation number 3 there. In terms of how this relates up to a net force equation, well, the only difference right here is we're still applying Newton's second law of motion, because if you have acceleration towards the circle center, then Newton's second law tells you also have a net force in that same direction. So if you have acceleration towards the center of the circle, then you must also have a net force that points towards the center as well. Okay, and that's what this vector would be. Now, a couple things about this. So that centripetal force is not a new force in the context of how we would draw this on a free body diagram. In fact, because we're dealing with forces, so we go to the same approach as I described in the previous lecture, which is anytime dealing with a dynamics problem with forces, we have to build equations. And to build equations, that comes from a free body and a mass acceleration diagram. Now, on the free body diagram, you do not write down a force as being Fc. All of the forces we talked about in the previous lesson, whether it's the force of gravity, the force of friction, the applied force, or the normal force, in specific scenarios, they may behave as the centripetal force, which is the force that causes the object to move in a circle. So we just have to identify in what situation are one of these 4 forces behaving like a centripetal force, and then that's the way in which we're going to draw it in a free body diagram. And then we'll approach the problem solving the exact same as we dealt with in a dynamics question. 2, the frequency, which we represent with the variable f, that is the number of cycles per unit time. It's typically expressed in a unit that's referred to as hertz. So going back to my rubber stopper example, if we had 2 hertz, okay, that unit hertz means cycles per second. So this would be 2 cycles per second. So in 1 second, if you had a frequency of 2 hertz, that rubber stopper would go around the circle 2 complete times. Now, there is an inverse relationship between the period and between the frequency. This is another equation on the formula sheet. We have t is equal to 1 divided by f. And this makes a lot of sense. Like, say, for example, you were to take the frequency and you were to make it bigger. So the frequency goes from 2 hertz to 4 hertz, in which case you now have to cover 4 full cycles in 1 second. Well, if you have to cover more cycles in a second, it means that the time to complete a cycle, which is the period, is actually going to be lower. So that's where you get the inverse relationship. Okay, if you make the frequency bigger, as in more cycles per second, then the period required to do that would have to be a smaller number for one individual cycle. Okay, let's look at a couple of example problems. So like I said, there's not really any difference in how we approach these problems in comparison to a dynamics one. The only difference is that we have equations for your centripetal, for your velocity or speed and your acceleration. But otherwise, we're going to write equations of the motion the exact same. Okay, so it says a car travels 20 meters per second, goes around an unbanked curve in which which has a radius of 122 meters. And I want to determine the coefficient of static friction between the tires and the road. And I want to identify 2 physics principles used to calculate in part A, list them in order of applications. Now, you might be wondering, like, why are we talking about static friction if the object's actually moving? Like, moving shouldn't it be kinetic friction? Well, it's kind of hard to describe the way in which your tire works, but uh, like in normal situations when like you're driving a car and your tire is just rotating, an individual point on the tire doesn't actually slide, and that's the condition that's required for kinetic friction to be implemented. Uh, so I wouldn't stress about that point there. But like if you just look at an individual point like on your tire, that individual point in your tire doesn't slide unless we're talking about ice, in which case you've got a massively different problem you have to worry about. Okay, but again, how do you get the coefficient of static friction, which is mu s? We don't have an equation we can pull it on the formula sheet, so we have to build an equation that's going to get this in here. All right. So let's go to, again, just the default process for a dynamics question. If you don't know where to start, is a free body diagram. Now, I'll draw kind of like two different pictures here. So we can do like a top view, although that's not going to be the picture I'm going to use for my force analysis. But a top view perspective would just be like you have your car and it's just moving around in a circle like this. Albeit it's just going around a curve, so it's probably not going around a full circle, but for at least part of its motion, it's moving in that circular direction. So we can still say that it's following uniform circular motion. Now, the view I want to do in this problem is I'm going to do a side view of the car. And you'll see why. Okay, so let's start off the free body diagram. So we got FBD, side view of the car. Now, the ground to be located underneath the bottom. And again, I always just draw my objects as boxes because I possess no artistic talent. So if from a side view perspective, if we draw the different forces acting on this, we would have from the center of the object, we have the force of gravity pointing straight down. We're not accelerating in the vertical direction, which means that we need to have the normal force so it is perfectly balanced. Now, if you just have two forces and you know those forces are balanced, what you do need to do in communicating on a free body diagram is you have to show how the magnitudes of the forces compare to each other. And the way you do that is if I want to show that Fn and Fg are balanced, you just draw the force vector so they're approximately the same length. And you'll see in the next example problem how I can show what happens if they're not the same length and how we need to exaggerate that one force is bigger than the other. Okay, those are your two y direction forces from a side view perspective. Now, when you actually look at the picture right here and you have to identify, well, what's responsible for this circular motion? Well, you have to have a net force that points towards the center of the circle. So what exactly is the net force responsible for the circular motion in this situation? It's the force of friction. Okay. The force of friction is the thing that's responsible for you going in a circle. And this is why if it's really icy outside and you're actually like making a turn like this, if you don't have the static force of friction, you can't make that turn. The cars, you just end up following the inertia of the car, which is you just continue moving in a straight line and you actually slide directly off of the road. So we have to have a centripetal force towards the center of the circle. Otherwise, we can't have circular motion, which means that the force of friction needs to point towards the right. There are no other forces acting on this object. There is not an applied force. An applied force means someone would have to be pushing on it from the outside or pulling, and that is not happening. I'm also going to draw a mass acceleration diagram. So mass acceleration diagram, all we have to do is label the mass as a variable. We'll pick m here and just draw what direction you accelerate in. Now, if you look at the free body diagram, there's only one force that is not balanced, and that force is the force of friction. So according to Newton's second law, you have to have acceleration in the same direction. The only difference here is I'm going to add a subscript c just to tell me it's centripetal acceleration, acceleration towards the center of the circle. Now, note here, I did not call this force of friction Fc, okay? The force of friction will be the centripetal force. We don't label Fc on a free body diagram. Now, again, it's not very clear where to start here. So uh, the coefficient of static friction is going to be calculated from this uh, this variable specifically. Okay, so we want to get it from FF would be equal to, and if we're talking about the maximum amount of static friction, it would just be mu s times Fn. Okay, that's the maximum static friction. Okay, all right. So the problem is, so if you look at the actual way I've drawn the picture, and let's just call this the y direction, and we're going to call this the x direction. Okay, but this is in the direction where the center of the circle is. So instead of calling it the x direction, I'm actually going to call it the c direction, the centripetal directions. We'll call that c here. Now, if we start in the centripetal direction and try to calculate the force of friction, we're not going to be able to do it. The reason we can't do it is because we don't know what the normal force value is. So we need to figure out what that is first. So we have to start in the y direction to figure out the normal force. So let's write an equation in that direction. So we're going to say up is positive, and I'm going to look at the sum of the forces in the y direction. In the y direction, we have no acceleration. And the reason we have no acceleration is because Fn and Fg are perfectly balanced. Okay, so that's equal to 0. And I'll just clarify that. Okay, so this statement is true because the forces are balanced. Okay, now we expand the equation of motion. Okay, so what this means again is look at the FBD. If the force points up, put a plus in front of it. If it points down, put a negative in front of it. So this equation of motion would expand to Fn, would be positive because it points up, minus Fg, which is negative because it points down, and then this would be equal to 0. Well, we don't know what Fg is, but we don't know what Fg is, so I'm just going to take it and I'm going to expand it one step further. So you're going to have Fn minus mg is equal to 0, and then we'll get an equation for the normal force. So we'll have Fn is equal to mg. Now, some people might look at this and begin freaking out because they're like, well, wait a second. I don't know what the mass is. If I don't know what the mass is, how can I calculate the normal force? Well, this goes back to my point that it's not good practice to sub in numbers until the end of the question. And you're going to see why this is important in this problem. So I can't calculate the normal force right now. So what I'm going to do is I'm just going to box this equation, and I'm just going to call it equation number 1. Okay. Can't really do anything with it right now. I do know what G is. G would just be 9.81 meters per second squared, but I intentionally did not give the mass in this question. Okay, now let's go to the x direction. So let's say that right is positive, and I'm going to find the sum of the forces. Now, instead of calling it the x direction, I'm going to call it the centripetal direction because this is the direction where you actually have a centripetal force. So sigma Fc, and this is equal to mass times centripetal acceleration. Now, if you replace the x or y's with a c, well, we're no longer just talking about accelerated motion. We're talking about a very specific case of it. And that specific case is uniform circular motion. Okay, let's expand the equation of motion now. So this one's pretty easy. It's not really even a sum on the left-hand side. If you look at the centripetal direction, the x direction, there's one force, it's FF, it points towards the right. So we write down positive FF is equal to, and then we have m times, and again, we have to be careful with acceleration. Acceleration points towards the right, so we're going to make that positive. So it's going to be positive AC. Now, I'm going to take this a step further. Okay, I'm going to do a couple of things. So, force of friction. If we're talking about maximum static friction, so this would be like the fastest speed the car can like go around the turn. We're going to take this equation and replace FF with it. So we're going to have mu s times Fn is going to be equal to m times AC. Now, I don't know what the normal force is, but what I do know is I have a mathematical expression for what it is. So I'm going to take this equation for Fn, and I'm going to substitute it in right here. Okay, let's see what happens now. If you do this, you would then have mu s times mg would be equal to m times. Now, we have another problem that I don't know what the centripetal acceleration is, but I do know what the speed is. So this is what I was saying. Like, you solve these questions exactly like a dynamics question, except you have some extra equations for speed and acceleration. So what you know in this question is that we'll go to the formula sheet and pull this equation off. We know that the magnitude of your centripetal acceleration, this is from the formula sheet, is equal to, and it is v squared divided by r. So let's write that down here. So it would be v squared all divided by r. Now, I'm just going to drop the absolute value of the vector and just write it as AC is equal to v squared over r. So just AC like this would just mean the magnitude of the acceleration vector. So instead of writing AC here, I'm going to replace it with v squared over r. So it's going to be mv squared over r. Now, what about that mass problem? Well, what you'll notice right here is that on each side of the equation, you have an m. If you have an m on each side of the equation and each term, you can actually cancel them off. Because if you were to divide both sides of the equation by m, divide both sides of the equation by m, it actually makes the m go away. So I don't actually need to know what the mass is to solve this problem. But again, if you try to sub it in right away, you have a big problem because then you'd be stuck and you wouldn't know what Fn is. So again, good practice is we don't sub numbers in until we get to the end of the problem. So the equation I'm left with now would then look like, we've almost got our solution. So we have mu s times g would be equal to v squared over r. Now, I want to get mu s, so I just have to divide both sides of the equation by g. I don't need to show that manipulation. So it would just be v squared divided by r times g. And let's plug the numbers in. So v is 20 meters per second. And we're going to square that. Yeah, anytime you sub a number and put it in its own set of brackets, if you wrote it like this, if you said 20 meters per second squared, that's wrong, okay? Because that's telling me you're just squaring the seconds unit, but you're not actually squaring the 20 or the meters. So all substitutions in brackets. Okay, divide this by r, which is 122 meters. And then multiply this by the acceleration due to gravity, but just the magnitude, okay? We already dealt with the fact that g is negative right here, okay, in this equation of motion. So meters per second squared. And your coefficients should have a value that's always between 0 and 1. Usually, most of the time. I think there's like some weird situations where it isn't, but usually it's between 0 and 1. So this would give you two significant digits. Again, you got two numbers. One's 2 SDs, one is 3 SDs. You take the lower number of significant digits. So it'd be 0.33 as your coefficient of static friction. Okay. And then it says identify the two physics principles used to calculate A and list them in the correct order of application. Well, look at what I did here. So the first thing we did is we used this equation of motion. Okay. This equation of motion, that is F net is equal to 0. So if we're doing a numerical response recording, okay, the first physics principle I used is we had to use F net equals 0 to get an equation for what the normal force is. So that's 0 there. Okay, what did we do second? We used this equation. What's this equation? Now, again, you might be tempted to say it's accelerated motion, but this is a special case of accelerated motion because we have the C's here. So this is uniform circular motion. So if we go back to our physics principles here, we're actually making use of this principle, which is principle number 2. So in the correct order of application, we used uniform motion, F net or sigma F equals 0 to get the expression for the normal force. And then we used the uniform circular motion equation to eventually figure out what the coefficient of static friction was. So in order, principle 0 followed by principle 2. Okay, let's do one more. So I have a 1.8 kilogram object is being swung from the end of a 0.50 meter string in a vertical circle. So a vertical circle just means that the direction in which you're spinning would be perpendicular to the ground, okay? So this actually matters because the force of gravity is going to have an effect on what's happening here. Now it tells me the time of revolution, which is the period. It's 1.2 seconds, and it wants me to calculate two things: the magnitude of the tension of the string at the top of the circle and at the bottom of the circle. Okay, so again, there's no equations. You can pull off the formula sheet to do this. You have to build your equations. So let's start with part A. So how do you build the equation? Free body diagram. Okay, what I'm going to do is I'm going to draw the object at the top of the circle. And on my free body diagram, if the circle is in the same plane as the free body diagram, I'm actually going to draw the circle with a dashed line. So we have this rubber stopper. We're spinning it around in a circle. So your FBD looks something about that. I could have had the dashes actually meet up at the top right there, but you get the point, okay? We'll use a little crosshair just to represent where the center of the circle is, and then we'll draw our forces now. Okay. There, it looks a bit better. Okay, so you're spinning this thing in a circle. We're spinning it in a vertical circle. So this is like a side view perspective of like spinning it. And again, the circle would hit the ground, intersect the ground at a 90-degree angle. It's perpendicular. So what forces do you have here? Well, you definitely have the force of gravity. Okay, this is the force of gravity points straight down. So you have Fg. Now, the other force you have is you have the force that the string would be exerting on the rubber stopper. Okay, that's an applied force. Okay, or you could call it a tension force as well, but it's an applied force from the string on the rubber stopper. Now, in terms of what direction that is, just ask yourself, if you were the rubber stopper, okay, and you're being spun around in a circle, would you feel the string pulling on you towards the middle of the circle, or it would be pulling you away? And you would definitely feel the tug of the string towards the center of the circle. Oops, had that issue with the vertical line there. It makes me seem like I have too many forces. But yeah, you would feel it pointing towards the center. Now, I know in a free body diagram, you should technically be drawing both forces like from the center of the object, but because the two force vectors point in the same direction, well, they would overlap and that would be messy. So you kind of just have to stagger them just a little bit. So we'll call that FA. Okay, we'll also do my mass acceleration diagram. I find in the circular motion questions, this is where it's really important to identify the direction of acceleration is. Okay, so let's draw my little dash circle. This dash circle is not technically part of the FBD. Okay, it's just there to kind of like help me illustrate, understand what's going on. Okay, rubber stopper at the top. We'll label the mass, and the acceleration is easy for circular motion. The centripetal acceleration always must point towards the center of the circle. Okay, so we have AC here. Okay, so now let's go ahead and write an equation of motion. Now, here's the thing. If you look at the FBD and the MAD here, if you make up the positive direction, you're going to have to write down every one of these variables as being negative because FA points down, FG points down, and AC points down. So sometimes it might actually be more convenient to pick a different direction to be positive. So here, in the vertical direction, instead of saying up is positive, I'm going to choose down to be positive. Now, if you choose up to be positive, you're still going to get the same result, but I just want to play around with fewer negatives. So we have down is positive. We're going to look at the sum of the forces in the centripetal direction. It's the y direction, but the y direction contains the centripetal forces. There's actually two centripetal forces here. Okay, and this is equal to m times AC. So actually, and this is why we write down sigma FC. So this means the sum of the centripetal forces, both the applied force and the force of gravity are helping out here, okay? They're both assisting in making this object move around in a circle, which is going to be a major difference compared to what happens at the bottom. Okay, let's expand this equation of motion. So look at the centripetal direction, which is the y direction. If the force points down, put it as a plus, points up, put it as a negative. So FA points down, down is positive. So we have positive FA. FG points down, it's also positive. And that's equal to M. And again, you have to be careful. Acceleration's a vector too. So we're going to write that down as positive A times C. Okay, let's expand this a little bit further. So this would be FA. I don't know the force of gravity. I do know the mass this time around, and you actually do need to know the mass in this question. Okay, so FG is M times G, and this is equal to M multiplied by. Now, the thing here is it tells you what the period is, not the speed. So we want to make use of the other acceleration equation, and that's the equation AC is equal to 4 pi r squared divided by, 4 pi squared r. My bad. Let's fix that. Okay, 4 pi squared r, all divided by t squared. Okay, so this would then look like multiplied by 4 pi squared r, and then divide this by t squared. Okay, let's bring this up here and continue the work. All right, so I want to get FA by itself. I can do that just by moving mg to the other side. So I'd then have FA would be equal to, we would have, let's bring this m in here. We'll write it after the pi. So we'll write down 4 pi squared mr over t squared, and then minus m times g. Now, at this step, you could sub the numbers in and calculate it. But in addition to isolating for the variable in terms of that you want to solve in terms of the other ones, I also want to simplify the expression as much as I can. So there's just one extra thing I can do here to simplify this. You'll notice in both terms there's an m. I can factor that out. So you'd have FA would be equal to m. And if you pull that out, then you'd be left with 4 pi squared r over t squared. And then we're going to subtract g. Okay, now let's plug the numbers in. Okay, I manipulated it in terms of the other variables, and I simplified it by factoring. So now it would be 1.8 kilograms. Okay, multiplied by 4 pi squared times r. R is 0.50 meters. We're going to divide this all by t squared. So t squared is 1.2 seconds all squared. We're going to subtract in brackets 9.81. Again, anytime you substitute something in, just put it in brackets. Good practice. And again, don't sub in negative 9.81. We already dealt with the negative when we accounted for the direction over here. Okay, it's just the fact we said down is positive that made the FG positive this time. Okay, let's write this down. We'll say FA at the top would be equal to, okay, all the numbers presented here are two significant digits. That's going to give you 7.0 newtons. Okay, that's at the top of the circle. Okay, let's go to the bottom now. So again, what equation do we use? We got to build it. Okay, so let's do an FBD. Okay, let's draw my circle. Again, this dash thing technically isn't part of a free body diagram, but it's helpful because it just helps you visualize where the object is in the circle. Okay, crosshair. Crosshair. And let's draw at the bottom of the circle this time. Okay, now, I find that these circular motion questions, it's more helpful to do the mass acceleration diagram correctly because it's going to help me identify what direction some of the forces point. So we'll write down M here. I know centripetal acceleration has to be towards the center of the circle. Okay, that's a condition for uniform circular motion. Now, at the bottom of the circle, we definitely have FG. It's still pointing down. Now, we do have an applied force. So here's the thing. When you look at the mass acceleration diagram, it tells me the centripetal acceleration is towards the center of the circle. So according to Newton's second law, I also have to have my net centripetal force pointing towards the center. So if FG is the only force pointing down and I have to have a net overall force pointing towards the center, it'll actually just tell you right away what direction FA has to point. Now, that's obvious because if you were the rubber stopper or being spun in a circle, you would feel the tug of the string pulling towards the center. But this also helps you identify which force is bigger. So we're definitely going to have an applied force towards the center of the circle. But if I'm going to have a tug of war winner towards the center to give me a net force towards the middle, which I have to have if I'm going to accelerate towards the middle, it means the applied force has to be bigger than the force of gravity. So think of this as a tug of war. If FA is up and it's bigger, FG is down and it's smaller, FA wins, and that's why we get to accelerate towards the center of the circle. Okay? So, as I said, if we have a couple of forces and I know for sure one is bigger than another one, you do have to communicate that by making one of the force vectors longer. Okay? You don't have to draw them to scale, but one of them does have to be bigger. Okay, now, before I even do a calculation, I could say to you, okay, before we calculate what the tension is at the bottom, where is the tension in the circle going to be larger, at the top or at the bottom? So if you think about it for a second, well, look what's happening here. At the very top of the circle, FA and FG are both pointing towards the center. They're both centripetal forces. They're both helping provide this acceleration. Now, in this scenario, FA is your centripetal force because it points towards the center, but FG is not helping. Okay. FG is actually trying to get you to go out of the circle. So in this case, this applied force has to work a lot harder to provide the same centripetal force and acceleration because FG is now working in opposition. So before we even do a calculation, we should know, qualitatively speaking, that the applied force at the bottom is going to be bigger. And let's see what happens if we do this mathematically. Okay, so first things first, pick a direction that it makes sense to be positive. Now, you can switch it in a different part of the question. So the top part of the question, it made sense to make down positive. Well, look at the diagram here. I have two vectors pointing up and one of them pointing down. So this time around, it makes a lot more sense to make up the positive direction. In fact, what I would always recommend doing is I'd always recommend making the direction you accelerate positive because then you don't have to worry about plugging in like the positive sign beside the acceleration term when you actually throw it into the equation of motion here. Okay, so let's make up positive. So we have the sum of the forces in the centripetal direction, and that's equal to mass times centripetal acceleration. So this is the circular motion physics principle. By the way, just another reason of why I do a free body mass acceleration diagram. The free body diagram is the sigma F representation of the equation, and the MAD is the mass acceleration representation of the equation, okay, for Newton's second law. So they're just visual representations of sigma F for the FBD and then mass times acceleration for the MAD. So it's just linking a picture to the actual equation you're going to build. Okay, let's expand this. So we've got to expand both parts. Okay, if we point up, the vector is positive. So looking at the FBD, FA points up, it's positive. FG points down, it is negative. And then this would be equal to M times AC points up, it's positive. Oh. fix that. And let's do the same thing. Let's expand and get FA by itself. So this would then be FA minus FG is M times G. This would be equal to M times AC is 4 pi squared R over T squared. Okay, let's add mg to the other side. And then we would have FA is equal to, let's move that m, so it's after the pi squared, so 4 pi squared mr over t squared. And this time we're going to add mg to both sides of the equation. We'll take it one step further and just simplify it. So I'm going to pull out the common m, and then I would have this would be equal to m. And then I'm left with 4 pi squared r over t squared in the first term, and then plus g in the second term. Now, look at how the two equations compare now, because you can actually see like why things are going to change quantitatively. The only difference between this equation at the top and the equation at the bottom is this single operation symbol. So for this equation of motion, we're subtracting g, and for this one, we're adding g. And that's what's going to make the applied force bigger at the bottom of the circle, aside from the fact that we could have already described that qualitatively, because we know the applied force has to work harder at the bottom to provide that net centripetal force towards the middle. Okay, let's plug the numbers in. So we'd have FA would then be equal to M, which is 1.8 kilograms. And again, make sure you're putting your units beside every number. Okay, multiply by 4 times pi squared times r, which is 0.50 meters. Okay, divide this all by t squared, which is 1.2 seconds, all squared. And then we add g, put it in brackets, 9.81 meters per second squared. We do not need to write down negative 9.81. We've already accounted for the direction. And then the magnitude of the applied force at the bottom. So we'll say FA bottom is equal to, this will be quite a bit bigger. And the number I got here is 42 newtons, although I think it might be 43. So let me do a quick check. So 4 pi squared multiplied by 0.5 divided by 1.2 squared plus 9.81 times 1.8. It is 42. Okay. So 42 newtons. So again, just look how do I solve this. It's identical to how I solved a dynamics question. The only difference is when it came time to deal with acceleration, we have other equations we can use to plug in, just based on what the radius of the circle is, or what the period of the object moving in the circle is, or what is its speed. Otherwise, we're just solving a dynamics question. All right, that's it for this lesson. And then we'll finish off the review of physics 20 stuff in the next lesson by talking about the final two physics principles, which are the work energy theorem and conservation of energy. And I'll talk to you then.